Okay, so we're back, and right now we're going to discuss writing the partition helper subroutine, and we're gonna see how to do this in a very high level, and then we're gonna go from there. So one of the analogies that I've been making is moving to a new city. And the best way to learn about a new city that you move to is to walk around with a map, because the map gives you high level guidance about walking around. And so we're going to use that same kind of idea, walking up. What we're going to do is we're going to use different levels of abstraction to write this function. So if we look at the function partition helper, it takes an array of naturals, and it takes the array index and a natural, and the natural is going to be the target that we're trying to reach. So effectively, there's two things in our function. There's the array itself and this target value that we're trying to hit. And the question is, like, how do we figure out what to do? And this is where data-driven design comes into play. So let's think about the array. So when we have an array, we can define it in a certain way. So we can say an array of naturals is in one of two states. So we can say that we've gone through the array and we've seen everything. So we can call this state out of the array. And the other state we can say is that we're in the middle of processing. So when we're in the middle of processing, we're at an array. We're at the array at a certain index. So array element at index I. And there's also the rest of the array that we have not seen. Rest of So this is I keep saying this is a high level view. So let's try to look at this in sort of picture form. So let's take a look at this array. So I took out the numbers because we're at a high level. It's like a map. So if we look at line 10, we're saying the array of naturals when we're processing is in one of two states. So we're either out of the array. So as you can see on the far left, we've processed everything, and that's one state. Another state is that we're at some arbitrary index I. So suppose the arbitrary index I is this green box. So we're at this box, and we still have the rest of the naturals to process. So everything in the purple box. So essentially, what we have is we've already processed these two red boxes, and now we're processing this green box, and we have these purple boxes left. Now, the purple boxes plus the green box is also an array too. So even though we've gotten rid of these two things, we're still an array. So that's why we still have the rest of the array of naturals. So I hope that makes sense. So at a high level, we're in two kinds of states with the array. And so now we have a target too. So we have the other variable that we have. So what is target? So target, we're trying to hit a target value in our problem. We're trying to see, when we're trying to do this partition, we find what the sum of the array is, we divide the sum of the array by 2, and then we check if we can hit that sum of the array divide by 2 number, and that's our target. And so the target is always decreasing. And our goal is that if we can get enough numbers such that the target hits 0, then we know we can partition our array into 2. And so if we think about it, our target is in a couple of states, right? So so we notice that we only care about when target is at 0. So when target's at 0, we know that we've gotten our answer. So target is 1 of, it's 0. And then target can be also another like positive number. So it could be, say, half of the array sums to 10, right? So then the target can be 10, it could be 9, it could be 8, it could be 7, it could be 6. So we could generally say that it's a natural number. The target itself is a natural number greater than 0. And the question is, like, why wouldn't you just say target is just, from 0 to 10, or it's like all numbers? Why did I make a distinction between 0 in line 16 and the rest in all other numbers in line 17? Well, the reason for this is that we have to think about where is our behavior changing. So when the target hits 0, we want to do something very different because we reached our goal than when the target is a different positive number. So these are our two different states that target can be at a high level. Now we're looking at it as a map. And so we see that our array can be written like this in line 10, and our target can be written like this. And so we're going to use the interaction of these two high-level views to try to figure out how to code our function. So we could write this, rewrite this, as a cross product of type comment tables. So at the top is target, which is 0. It can be either 0 or a natural greater than 0. And then for the array, which is on the left-hand side, it could be out of the array, or it could be like the array I is like the green box, and array colon I represents the purple box. So in Python, when you want to write like the rest of the array going from right to left, you use this colon I. It's the way to say the prefixes of the array. So now we make this table and we try to understand what's happening in our function. So let's think about this. So let's look at box 1. So in box 1, what's happening is that we've processed all our elements. So we're out of the array, and the target is 0. So what does that mean? We've hit our target and we've processed all of the elements. So that means that, like, it's true that our array can be partitioned into two separate subsets. So this we write true. Box 1 is going to be true. So let's look at box 2. So we've gone through all the elements, but we still haven't hit our target sum. We haven't hit 0. Like, our target to make this partition happen hasn't happened. So in box 2, we write false. Now let's look at box 3. So box 3, our target is 0. Like, we found a subset. This means we found a subset that of the array that is half the total sum of the array. And we still have other elements to process, but the thing is that since we already have all the elements that are in one subset, and by design of the problem, we figured out the target, the initial target, by dividing the total sum by 2. We know that in box 3, if we've hit the target 0, like that, it's definitely true that this array can be partitioned into two separate subsets. And now the more difficult thing is box 4. So box 4 is sort of like the most difficult part of this. Like, okay, so what does it mean? So we're somewhere in this array. So we're supposed in the green box, and we have all the purple boxes left, and we have a target greater than 0. Now, recall earlier we talked about that picture that we had with induction, right? We had a domino, and we wanted to see if it would fall based on whether the domino on the left or the domino on the right would knock it down. So let me see if I have this picture on me. So it's right here. So in this picture, what we see is that we're trying to decide whether. Remember the decision that I was saying at each box was determining if we should take the integer into our subset, new subset, or not take it. And so we have two options. So if I take the value into my subset, my set. So that would be like, if I take, so in this example, I'll just copy this. Okay, let's do the bottom. So if I take the value into my subset, so if I take 5 into my subset that I'm keeping track of, then what I'm left with is a new problem. I'm left with a smaller problem of partition helper with array, and I've moved from the green box to the purple box. So I'm at index I minus 1 now. And my target value has changed. So my target is now I have to subtract this last 5. So that's what I do there. And if I choose not to take the value into my subset, then what I'm left with is partition helper. I still go to the purple box after the green box that I'm looking at, and I am left with target, this same target, because I didn't take that element, this is my subset. Now, these are my two, so it can be one of those two things, and I want to find out which one of these two smaller problems, because if you look at it, the purple boxes on the figure, it's a smaller version of this bigger problem with a different target value. And so if either one of these two actually is true, that means that I can definitely partition my set that I'm looking at right now into two separate things. So what I want back is I want the domino that's going to knock down my bigger problem. So what I'm going to be able to return is the best of this or this. So now, if we look at this, so let's see. So let me just move this, because this was in box 4. So we can see in box 4. So we have to take the best two of these. So in box 1, so let's look at our example. So if we have 5, 11, 5, and 1, so if I take 5 into my subset, then the total target sum that I'm trying to hit is 6. And then what's going to happen is that my target is 6, and I'm still in the array. So I'm in box 4. So then my function is going to try both things, the thing in line 27 and the line in 28. And so now we have these boxes, but these boxes represent cases. And so now we have a high-level view of what to do. And so essentially, I can make all of these into if conditions in my function. So, like, if we're out of the array, if we've processed all the elements and the target is 0, then we know from box 1, if, like, we're going to put true. If we're out of the array and the target's still positive, that means that, hey, we can't do this. This is not possible to partition 2 subsets. And if we're in the case where, like, hey, we've hit the target and there's still some elements to still process, it's okay because we've hit our target, so we're going to return true. And then in box 4, we're in the middle of the array, and the target's still positive. I want to try accepting the element or like not taking the element, and I'm going to choose the one that's best. And if one of them is true, that means that if I could partition the smaller subset into 2 subsets that hit this smaller target, that means that I can partition my bigger problem. And so that smaller problem is going to knock down my bigger problem. So in the next video, what we're going to do is we're going to take these conditions and write the function. So we're going to move from the higher level map that we just created into the actual walking, which is writing the function.